All good on my side.
All right, so let's start the session. We have Loïc Pujet, who will tell us about Hurewicz and Brouwer.
Thank you. So this is joint work with Axel Ljungström, as you have grown to be accustomed to for this session. And even though my title is about these two old guys, I should come clear right away and say this is not a talk about the history of mathematics. The more honest title would be that it is about the Silla-Hurewicz theorem in constructive hot. But you know, that's a bit boring. So when I was preparing my abstract, I looked up the biography of this Hurewicz guy, and it turns out that he was an assistant of Brouwer. And since Brouwer is the father of intuitionism and arguably constructivism, then, and we are doing like Hurewicz theorem in constructive mathematics, I felt like this was a nice way of reconciliating these two guys, because I think Hurewicz was not really interested in Brouwer's intuitionism, even though he was his assistant, and Brouwer was a bit sad about it, maybe. So yeah, this is a happy ending. Anyway, so the theorem we are set to prove is this thing. So if X is a n-1 connected CW complex, then the abelianization of its nth homotopy group is the same as its nth Silla homology. So these are lots of words that you might not all be familiar with. Yeah, I mean, connected hopefully is good. It's just that its n-1 truncation is contractible. CW complex, I will explain a bit later, and homology likewise. Okay, so later is now. And a CW complex is some kind of type that you can build inductively by attaching cells of increasing dimensions. So you have this kind of filtration starting in dimension -1, then dimension 0, then dimension 1. And so the dimension -1 is defined to be empty, it's just here for convenience. The dimension 0 then is a set of points. Then in dimension 1, you glue some, I mean, one-dimensional disks, so really some edges on these points. Then in dimension 2, you glue some two-dimensional disks between these edges, and so on and so forth. And this gives you a family of types, which is quite versatile, because when you have these kind of presentations, you can do your constructions inductively on dimensions and also cell by cell. This is very easy to translate to homotopy theory. You just use push-outs to represent this kind of gluing operation. And there's a small caveat, if you want to say constructive, is that in our construction, we will generally need to do to use the axiom of choice or some principle of choice for families indexed over the sets of cells, because we want to do something for every cell which is not necessarily homotopy coherent. And in general, we do not have the full axiom of choice in constructive hot. So the one option is to just work with finite CW complexes. If we want to be a bit more general, then we can say, yeah, we can work with any CW complex for which these sets of cells satisfy the choice principles that we need. So this is the good old constructive trick of looking at what you need and putting that in a definition and calling it the correct constructive notion. So in that case, it's called projective. So yeah, for the rest of this talk, I will only discuss projective CW complexes. Okay. So one of these definitions that you can do inductively on the dimensions is homology theory, which is very nice to describe. Like, it's a super classical thing in algebra and topology. Everyone sees this in their first course, or maybe a singular version, but whatever. And so, yeah, to any CW complex, you can associate a family of abelian groups indexed by the natural numbers that we call Hn with a little CW to signify that it's the cellular homology of X. And the idea of these abelian groups is that they measure in some way the number of n-dimensional holes of the type X. And furthermore, even though their definition uses this cellular structure, we can prove that they are completely independent of the particular cellular structure that you picked. So if you have two different cellular structures on X and Y, or on X and itself, I mean, then you will get the same family of homology groups, and it's homotopy invariant, it's functorial, I mean, and it satisfies the whole Eilenberg-Steenrod axioms, which is just a list of properties that are completely standard for homology. All right, so I just said that these homology groups kind of count the number of n-dimensional holes of a space, but this is also how we kind of get intuition about the homotopy group of X. So what is the difference? Well, there are some differences in terms of definitions. Okay, I mean, this is the homotopy groups are just defined as truncation of the loop space, and the homology groups are defined using this structure. Then, for instance, for products on the side of the homotopy groups, then it just like commutes with products, I guess. And we have this kind of Pujet formula for the homology groups, which looks a bit more complicated. And I guess the major difference is how you can compute the groups of a space by separating it in several pieces, computing the groups of the pieces, and then putting everything back together. For homology, it's very simple because you have this property called excision that I will not get too much into. And for homology, it's actually much more complicated because you have only a kind of lousy version of excision, which is called the Blakes massive theorem, which works a bit less well. And for that precise reason, we have a very good idea of what are the homology groups of the spheres, but the homotopy groups of the spheres, I mean, in the previous talk, you saw that it was very complicated. So yeah, there are some differences, but yet these two invariants are related by Hurewicz theorem, which says that once again, if X is n-1 connected, then the abelianization of its n-dimensional homotopy group is the same as its n homology group. So how do we prove that? Well, the way we do it is notice that there is a family, a subclass, I should say, of CW complexes for which this theorem is very easy to prove. And these we call, I don't know if it's something that appears in the literature, we kind of coined the term Hurewicz n-connected, which is kind of the same as being n-connected, but in terms of the cellular structure, not in terms of the resulting space. So we say that a CW complex is Hurewicz n-connected when it has exactly one zero cell, so exactly 1 point, and zero k cells for k, which is smaller or equal to n. So to take a non-example, this guy is zero connected, but it's not Hurewicz zero connected because it has plenty of points, even though they are all in the same connected component. This guy, on the other hand, is Hurewicz zero connected because it has only one point. So this is just the property of the cellular structure, not a property of the space. I mean, you can phrase it as a property of a space by saying that there merely exists one cell structure that is Hurewicz and connected. Anyway, point is, if CW complex is Hurewicz n-1 connected, instead of the usual statement, which was just n-1 connected, we do have the Hurewicz theorem, which follows quite straightforwardly from the Blakes-Massey theorem and the excision property for homogeo. Basically, what we do is that if we know that X is Hurewicz n-1 connected, we have a very nice presentation of it with no lower dimensional cells. So we can just like compute pi n of X and hn of X in terms of the cell structure. We do that using the Blakes-Massey theorem and the excision theorem on each side, and we notice that they coincide. Okay, good. So this is not quite what we wanted. We want the same thing, but without the Hurewicz in the statement. So now what we want to prove is that every CW complex which is n-connected is equivalent to another CW complex which is Hurewicz n-connected. Okay, so this is some very classical thing in algebraic topology, I guess. But I should time. So, I'm doing very fine. I can slow down a little bit. So if you try to do it too naively, it does not work all that well, because the classical strategy would be to just forget about the CW structure that you add on X, and then just add a new one by taking what you need. So you say that the new set of n+1 cells for X will be just a set of generators for its n+1 homotopy group. I mean, this should work, right? But the problem is that if we want to do that with our finite or projective CW complexes, well, we need to show that pi n-1 of X is finitely generated when X is n-connected CW complex. Well, this is true because we can prove it using the Hurewicz theorem, but of course, we want to prove that theorem, so we cannot use that. So how should we do this? It's not so clear because if you remove the unconnected, then you have no hope that this holds. For instance, you have some finite CW complexes, such as, so with only a finite number of cells, such as the wedge sum of S1 and S2, for which some of the homotopy groups are not finitely generated and not even projectively generated unless like you have countable choice. Well, okay, then we kind of gave up on that approach and tried something else, something more pedestrian. So, okay, let's try to do it by hand. First, in dimension 0. So we have some kind of CW complex with maybe some higher dimensional cells, but I just draw its one skeleton. And we want to replace it by an equivalent skeleton or an equivalent one-dimensional skeleton, which has only one vertex. So what we could do is proceed by induction on the number of vertices. So we just look at each vertex, and in case there are more than 2, we notice that they have to be connected. There has to be a pair of vertices that are connected by one edge, and we can remove that edge one by one by induction. Okay, this is a bit pedestrian, but there are problems with that strategy. First, it uses induction on the number of vertices. So it only works for when we have a finite number of vertices. But we don't really want to assume that. We would like our proof to be kind of uniform in the finite. It should work in the finite case, you know, and it should also in the event that we have access to choice, it should apply to fully general CW complexes. Because if we have choice, then every CW complex is a projective CW complex. All right, so yeah, not great. And even worse, it's not clear how to do this in dimensions greater than 0, because, I mean, stuff starts getting complicated, there are compositions. Okay, so not such a great method. The method that will actually work is that instead of removing stuff, we are adding stuff. So we take that CW complex once again, and we pick some random base point that we can do at least merely. And then we add a new edge, well, a new point with an edge to that base point, which I wrote in blue. Sorry for the colorblind among you. Maybe I could have dashed it or something like that. And then after that, we add an edge for every vertex which connects it to this base point, including the one that we picked as the base point. So this one has now two edges, one blue and one red. And then this shape, which we might call X prime, is a bit interesting. If we try to mentally contract all of the edges that are in red, we note that every vertex in the one skeleton becomes a circle, really. And the blue edge that we added also becomes a circle. So the whole thing becomes equivalent to a wedge sum of circles indexed by C1, which is the number of one-dimensional edges, and +1 for the blue edge. But then if we don't do that, and we instead contract the blue edge and use the connectedness hypothesis, then we can note that X prime is also equivalent to X1 plus a wedge sum of all the red edges. So this time there are not C1, but C0, many of them, since there is one red edge for every vertex. So C0 is the number of vertices, of course. Okay, so if we put this together, we get that this thing, which is almost X1, so X1 plus some wedge sum of circles, is equivalent to a shape which is just a wedge sum of circles, so which is, by the way, Hurewicz zero connected. And then we can fix this slight mismatch by just adding a bunch of 2 cells to kill the extra circles in the left side. And adding 2 cells on the right side will preserve the fact that it is Hurewicz zero connected. So yeah, by adding this 1 cells and 2 cells, we can get a presentation of the one skeleton of X that is Hurewicz zero connected. Very nice. And the good thing about this strategy is that it generalizes very well to dimension n. So we can do more or less the same thing if we start with some CW complex, which is n connected, then in particular it is n-1 connected, and by induction hypothesis, it is Hurewicz n-1 connected. And then we can do the same kind of trick without the blue thing, because there's always a distinguished higher cell, which is the trivial one. Okay, so we can show this kind of equivalence between something that is almost the n+1 skeleton of X and something that is Hurewicz well, which is just really a wedge of circles. And then we add some n+2 cells to kill the extra stuff that we have on the left side. And yeah, that works. It's not very complicated, but it's quite different from the classical proof. So we thought it was interesting. We have constructively that every n-connected CW complex is equivalent to one that is Hurewicz n-connected. And as a consequence, that if X is n-1 connected, then the Hurewicz theorem holds. We have an easy description of its n-dimensional homotopy group. This was all done kind of in view of applying it to the project of formalizing the self-finiteness theorem that was started on paper by Barton and Compion, I think, and then Milner started a formalization project. So hopefully it should be plugged into that project at some point. Okay, thank you for your attention. Any questions for me?
So, I was wondering, well, first of all, there has been a paper by Christiansen and Skokola about the Hurewicz theorem and homotopy type theory. So how is your work related to that?
So that one does not use cellular homology, but rather the, maybe I should call it Eilenberg-MacLane homology, which is defined in terms of spectra. And so, I mean, it also proves the Hurewicz theorem, and the difference is just that it's a difference between the two homology theories. In ours, it's a bit easier to do some computations, like we hope that it's easily amenable to explicit computations via linear algebra and stuff like that. Plus, we have a proof of additivity for for projective index sets, while in the case of the Eilenberg-MacLane homology, additivity is still an open problem, as far as I know. So we have some things that we know how to do a little bit better, but otherwise, these are two completely different strategies for something that is similar.
We also have another question. So actually, Clemens Berger, in his PhD thesis, actually his PhD thesis was like about an effective proof of the Hurewicz theorem, which is, is not in the context of homotopy type theory. So I'm not sure. I don't think this is particularly well known, but I'm just was wondering if you were aware of this result. Actually, I think it would be quite interesting to sort of go back to this sort of effective proof in a more traditional sense and see in which sense the results are related.
Yeah, we were not aware. Thank you for the
reference. Yeah, sure.
Yeah.
Anybody else?
Yeah, can I ask a question from Zoom?
Yeah, okay.
Yep. Yeah, it's Dan Christensen. Yeah, can you say more about what's known about the comparison of the cellular homology and the Eilenberg-MacLane homology, say for finite CW complexes?
In the case of finite CW complexes, I think they should coincide since both of them satisfy the finite Eilenberg-Steenrod axions, and that should be enough to fully characterize them on finite CW complexes.
Right. So then the difference between the results would be for projective CW complexes, where we don't know they agree?
Yeah, I guess, yes.
Yeah. Okay, great, thanks.
Okay, and we have one more over here.
So, could you explain again this part of the proof where you contract the blue edge and then you get a bunch of every vertex gives a loop?
Okay, so if you contract the blue edge, then the North Pole becomes attached to the one skeleton, right? And then you can use the connectedness hypothesis to merely bring all the south poles of the red edges back to that blue point.
Right. So you have to merely choose all these paths, and this you can do because of that.
Yeah. In the end, oh yeah, I was not very careful with that, but our theorem is that is merely equivalent to a Hurewicz unconnected CW complex. So yeah, everything is done up to truncation.
Right. Any urgent question? No? Okay, then let's thank Loïc one more time.
Thank you.